Okay, let's look at 2D scenario. So if you look at 2D scenario, you have added one more direction. Just now in 1D dimension, we discussed about X direction. Now we add one more direction for 2D dimension, two-dimensional heat conduction without convection. So now we are still at the conduction mechanism. So what is different in the equation is that you just added one more equation in y direction. Means just now in the equation you see qx and qx dx. Now you just added one pair of equation inside the equation that we discussed in the first session. So you just add qy and qy plus dy in the equation. Then it will become two-dimensional equation. All right, so this is what I mean. So just now the light blue is what we discussed in the first session. Now, if you're discussing about two-dimensional condition, you just add the yellow color equation inside. So you just add del over del y because the heat transfer happening in another new direction. In this case, is in y direction. So you just add del over del y, kyy, change of temperature in y direction, plus q equals 0. Okay. The derivation step still the same, only you add one more direction in y, you arrive at this equation, right? There's one more diagram on the lower left corner of your screen. So we will look at vector, what happened to the vector of the Q. Remember the Q, this one, the Q always, when we have positive, it's always pointing to the area, to the area.
Oh, sir, a moment.
Yes.
The exam is on 20th.
If it's about
September.
exam, discuss later. Okay. Yeah, we are now in the class. I already asked you question just now. All right. So we at the normal direction of your Q. Your Q should always have pointing into the surface with its positive Q. And if you look at this diagram, it is 90 degree to the surface. Okay, 90 degree to the surface. All right. And you have your y-axis, x-axis with the angle of normal. It means that if you split the object into half, you will see the diagram on the lower left corner. Okay, if you split into half, then you have the Q normal to the split surfaces half here. Then from the Qn, you know that Qn is a vector in this direction. You know that Qn you can split into two directions if you need it. So you can split in this one and this one. So in the case of y and x, you can split into y and x direction. So in this case, you see two arrows pointing down and pointing to the left. You split the vector of Qn. Okay. All right. Then after that, we apply the boundary condition to the equation above. What is the boundary condition we have? Temperature at the base of QB on S1. Surface 1, you can name as, let me see, in the diagram, I didn't show you the S1. Yeah? So if you look at the previous diagram, so S1 is one of the surfaces. So you can apply the same. So you assume this one is your S1. Okay. So surface 1, you have the temperature at base, TB. And then you do the same substitution. Your Qn will equal to Kxx del T over del X Cx plus the Y component equal to a constant on surface 2. Okay. So Cx and Cy, this one, we are looking at you need to split according to trigonometry direction, but you will see this one when it comes to tutorial, right? What is important on these slides is the equation above, right? So when you talk about 2D, you talk about X and Y direction. Okay. All right. The rest, I think you can read from your screen. What happens if you have conduction happen between solid and fluid? Then heat transfer will happen. Temperature will be different. Okay, this one happen in most of the case. So what does it mean? If let's say you have a pipe, okay, you have a pipe in blue color. Pipe is solid metal, and let's say you inside this pipe, you're having a hot liquid, a hot oil. Okay, a hot oil that flowing from left to right. So this hot oil will transfer some heat to the blue color surfaces through conduction. So some heat will transfer here, right? From here, go into the blue color solid metal, then transfer to the atmosphere. This kind of motion, it can either happen by two methods. One is force, one is natural. Force means you are using something mechanism, maybe pump or something, or anything that happen in natural. Okay, so you can force by using pump or maybe by gravity. Okay, something like that. So normally for heat transfer with convection, or we have done with we have done with conduction already. Now we look at convection case. So convection cases, we will assume the temperature change delta T is greater in X direction compared to Y and Z direction. So if you draw a control volume, or you can see from the right hand side cube. So right hand side cube, the X direction, the heat transfer happen in X direction is greater than Y and Z direction. Okay, so let's take note. When happen in convection, we continue to focus on X direction. Okay, based on what concept? Because we assume that the temperature change in Y and Z direction is smaller than X direction. Right? And if you look at the diagram itself, this diagram is for convection. Is a conduction plus convection. These are two. Okay, just now the diagram that you see, the equation that you see here is all fall under conduction only. Now the screen that you see, I'm showing you now, is the one with conduction and convection. Plus 2, and you see something happen to the diagram at the lower left of your screen. You see something H is added. Something H is added. This one, Q, is conduction. Meaning if the question asks you about conduction, then you only consider Q and also KXX and so on. If the question asks you to consider conduction and convection, then you need to consider H. Okay, H. You see the QH here? QH, it means that you're having a convection happening inside the control volume. Okay, so this is something new for second session, that you look at convection and conduction. Yeah, so something added to the control volume here, which is a H. If you see H, or normally in question, we won't tell you there's a H, but you will see either you need to solve conduction without convection or conduction with convection. So if you need to solve conduction with convection, then you need to add a H parameter inside your free body diagram. Yeah, so these are the key area that you need to focus on. If the question asks you to solve something with convection, especially conduction with convection, means you need to consider H inside your calculation. Okay. So for conservation of energy, I think you're familiar with this equation that we explained just now. If you see on the left-hand side is on the convection, sorry, on the conduction. You see the QX. This one also conduction. This one also conduction. However, when it comes to conduction with convection, there's something added to the equation. I highlight with blue color. You see, we add QH P dx over dt. Again, what is P? Need to take note. P is perimeter. P is perimeter. So you are good in calculating perimeter, right? Square, no problem, right? Circle is a little bit challenging for some of you. Perimeter of a circle is 2 pi r. Okay, so take note. When you need to calculate convection, then you need to add QH P dx dt to the equation. All right, now I put the equation on top. So again, if you see QX, Q, this one, all these are conduction. This one is convection. All right, now, and then you expand a little bit the equation. And we apply Newton's law of cooling to the equation. How we calculate QH parameter? QH given by this equation. QH equal to H times the temperature difference. What is H? H is the coefficient for convection. So this one, how you find the H value? Also in the material table, there is a parameter for convection. So we are using imperial unit. We are using imperial unit, K omega over m squared dot C Celsius. All right. And T is a temperature at solid. This one at solid or interface. And this one infinity is the fluid. Fluid temperature. Okay. So if you're having a pipe just now, this is T infinity. The fluid temperature is T infinity. Temperature at interface here, T. Okay. So there's a temperature difference between the fluid and the intersection or the surface of contact surface here. Okay. So when you need to calculate the convection, you are focusing on the intersection surfaces, the contact surfaces and the fluid. So you take T minus T infinity. Okay, T minus T infinity, solid surface temperature minus fluid temperature, and this is the convection coefficient. All right. Then we further simplify the equation above by again we dividing the equation both sides with a dx dt, means we divide all these things with a dx dt. All right, both sides also, here also, here also, here also. Then you arrive at this equation. Okay, you are seeing the blue color equation, del over del x kxx del T over del X, T temperature plus Q equal to rho C del T over del T plus H P. Again, P is not pressure, but it's a parameter of the area. Okay, parameter of the vessels, right? Or you can just see it as the perimeter contact by the fluid. Okay, perimeter contact by the fluid. It can take many different shape. Okay, this is the P parameter, right? And again, you need to polish up your differential equation skill or differential skill. So this equation is important. Okay, when you have conduction plus convection cases. Again, we added one more component inside our equation compared to the earlier session. Right? So we take this equation I put on the screen here. So as you can see here, let's simulate our scenario. So let's say we only have one area of convection, means the area was exposed to atmosphere and other surfaces was closed or insulated with material that not allowed heat transfer by convection. So normally this H, this component, you need to calculate when you have an open area. When you have open area, then you need to consider the H component or convection component. All right. So on the diagram here, you see that we added H here and S3 means surface number 3, and you have the temperature infinity, which represent the streamline. Okay. All right. So what does it mean? It means that this equation, if you only have convection in the system, then you need to consider the QH. Later, when you look at the tutorial, then you will see. Right? So this is just what happened. This equation is only happen on this diagram. For this diagram, this equation only apply for this diagram, where you only have convection happen at the end of the boundary condition of the control volume here. So you use minus kxx tx over dx equal to convection happening at the end of surface number 3, S3. Okay. So this is the chart that you will see in the exam. No, not exam. This one is just information that what are the unit for heat transfer analysis. For example, conductivity, temperature, heat flux, convection coefficient, energy, specific heat, density, so on. So on this side, it's important for you to always check your calculation, that you should use the correct unit. This is table 13.2. You will see in exam. This is the one that I mentioned, the K value, the KXX value, conductivity value. So if exam asks you aluminium, then you use 117. Sorry, not this side. This side, as unit SI. You use 202 if the exam are using aluminium solid material. Okay, and so on. So all this you can read lah. And if you're using fluid, then you use this value lah. If you're using fluid, if you're using solid, then you use this value. Okay. This is a table for convection, the H value. So you need to see what is the scenario you have in the exam. So if you're running with boiling water, then you are using a range. Normally, if the table is having a range, the value will be given in the exam. Okay. Yeah. So this is just a range for material for convection scenario for the H value. So you can see from this table, there's a range, meaning in exam, H value will be given. Okay, H value will be given. And before we end, just to recall that we have 7 steps for finite element analysis, it applies the same for heat transfer. Okay, then we will stop for today's lesson. So just recap. First, you select the element type. What I mean by first step number 1, you break your element into a few points. For example, what you see on the screen here, you break the surfaces into 2 points, point 1 and point 2, temperature 1 and temperature 2. And if you have a equation for your temperature, means you have a temperature 1 and temperature 2 with equation. T over here, T equal to constant value N times T1 plus constant value 2. T2 means you get a linear variation of your temperature. Then you can calculate what is the temperature at 1 and temperature number 2. Okay. So basically, what is step 1 in finite element? We choose the element type, means you break the element into points to then you label them with the length and point. Second one, you choose the temperature function. So in this case, I give you the more direct one with the linear equation. Temperature equation equal to T equal to N1 T1 plus N2 T2. So given you the form function for N1. N1 given you by 1 minus x divided by L. N2 equal to x divided by L. Okay, so this one derived by mathematics. So I already explained. You've seen this one before when we analyze for bar element. Okay, so in this case we also use the similar principle, but this time we look at temperature. Okay, in previous chapter when it comes to bar, you see this one as a displacement, but when it comes to heat transfer, we look at temperature. So from here, you have the N matrix here. Okay, you have the N matrix. So I think you are familiar when you try to write this equation in matrix form. So you can write the N in this matrix form. And you can write your equation in this form. Temperature equal to N matrix times the T. Okay, so T on the left hand side, curly bracket, N matrix that you see on the screen here, and the temperature matrix with T1 and T2. Okay, I think this one you're familiar with the transformation from the normal equation into matrix form. Step number 3, find the temperature gradient over temperature, heat flux, and temperature gradient. So this one I just straight away give you the equation. So temperature gradient given by the changes of temperature along a certain distance. So we differentiate the temperature over x, we get the gradient. Okay, the word gradient means normally in mathematics you take dy over dx. In this case, we talk about temperature, so you take the temperature divided by dx. Okay, so you can write as B matrix times T. Okay, so what is B matrix? B matrix is you differentiate the N1 matrix divided by X and N2 divided by X. Okay, so just remind yourself what is the N. N is 1 minus X divided by X. This is your N1. This is your N2. Okay. So when you differentiate them with X, you differentiate the first one with X, this one cancel, you'll get 1 over L. This one, when you differentiate over X, you will get 1 over L. When you differentiate this one, you'll get 1 over L. Okay, so there's a negative sign there. Right? So far we're still at mathematics operation. Then what about the heat flux? Heat flux given you by this equation, Qx over temperature gradient. We will use negative D matrix times the G, means G is the temperature gradient. So you combine this one into here, you'll get, okay, D is the metric property matrix, D equal to Kxx. So you substitute once you do the equation. All right, you will see this one in one of the tutorial questions where we will discuss maybe next lecture. Okay. Then after that, step number 4, what you do, you build the matrix again, given by this equation, right? I will not go into detail on how you get this equation you see on the screen, but this is the K matrix that we use. K equal to integration to get the volume. You use B transpose matrix, D matrix, and B matrix. And in the case, don't confuse with the B matrix that you learn in for bar and beam. Don't confuse. This B here is for conduction. What is B? What is D? that you see in the previous slides. Your B is this one, D is this one, D is KXX, K matrix. B is this one. So don't confuse with the bar and beam chapter. Then plus, if you see H means convection. This one is for conduction. If you have a convection, you have to plus the H there. Convection. Meaning, if you have a conducting rod and you seal with insulation layer and open to the space here, so these surfaces have a H. Okay, so the Q will come in, QX, and come out, QX plus DX plus H. So you have this equation, right? So if there's no convection, then you don't need to calculate this component. Okay, but normally if you have a opening, then you need to include the convection factor there. Okay, so again, this is a side note. First one for conduction, second one for convection. Right. So convection, this one is on the end. This one is for that particular location that is open to the atmosphere. So the surface here is this area, S3. So this one, this side is, again, what is your question? Go ahead.
So radiation isn't considered.
Again, repeat your question. I do not get you.
The radiation part isn't considered.
We haven't come to radiation yet.
Okay.
All right. Radiation will be in next lecture. Today we look at conduction, convection. Okay. Of course, radiation, they will have plus here, plus radiation. So we go slowly first. All right. Okay, so this one just a side note lah. When you consider conduction, you use this equation in matrix form. Kc means conduction. You use A, Kxx divided by L, 1 minus 1 minus 1, 1. While for convection, your K matrix is KH, represent convection, written as HPL divided by 6. Again, the P here is not pressure, but is a perimeter. It's a perimeter of the control volume or the contact perimeter by the fluid. Okay, contact perimeter by the fluid. P. L is the length of the boundary control volume. This is L, right? H is the convection parameter that I showed you just now. The matrix inside here is 2, 1, 1, 2. If you compare side by side, there's a differences between conduction and convection. Okay, conduction is KXS divided by L, 1 minus 1 minus 1, 1. However, for convection is 2, 1, 1, 2 times the HPL divided by 6. Okay, right. So later in next lecture, when you look at tutorial question, you will see how we use back the concept that we learned since chapter 2. We apply to thermodynamics chapter in this one, especially for heat transfer. The concept still same. It's only that the matrix that we use is a little bit different. Okay. So you're having these two equation, K equal to conduction plus convection. That will happen in this case, yeah. So point 1 to point 2 with one opening that exposed to atmospheric and convection is happen. Then you build the matrix by combining these two equations. All right. So if you have a free end, then you need to add one more matrices to your equation here. That's why you see this one actually when your n is opening, then you add this form. This is just a elaboration of why there is this term here. Okay. So this term is because you have n number 2 here exposed to atmospheric and convection is happening. So when we calculate for our matrix, we'll include the H factor inside. So you have two components there. All right. So let's look at only additional convection term where give you the KHN here. And there's a derivation of equation. You integrate 2 times to get the surfaces, because one is integrate x direction, one is integrate y direction. So dy dx you get area, okay? Because surfaces is area. So h is the convection factor coefficient, n is the form factor given by the screen here. One is transpose, one is without transpose. So if you substitute the value, the n transpose, you will get this function after you substitute the boundary condition that you see on the screen here. All right. So your n equal to n1 equal to 1 minus x divided by L. So n2 equal to x divided by L. So what happened at the end here? The boundary condition here, what is the value of your x? X equal to L, because this is x equal to 0. The length is L. So this is 0, this is L. So you substitute your L here. L divided by L is 1, so n1 equals 0. N2 also same. X equal to L, so you get 1. So that's why you get 0 and 1 here. And then you do the transpose, you write 1, 0, 1 like this. Okay. So you will get this term. If you this one times this one matrix, you get 2 times 2 matrix. You get 0, 0, 0, 1 times H times A, right? So because ds is area. Okay, because if you integrate dx and dy, you get area. So at the end, you get HA and the product of matrix 0, 0, 0, 1. Okay, so another one is that convection forces. If you need to find the convection forces, now it's about force. How you find force? you straight away use the equation that you see on the screen on yellow color. So what does it mean? You use FHN means convection forces. Convection forces we write as FH equal to HN. Again, how you differentiate conduction and convection. So as long as you see convection, you use H. T infinity, again, what is infinity is a fluid temperature. Fluid temperature times the area and times the matrix 0, 1. Okay, 0, 1. So this is fixed already. Basically, if you need to find convection force, you just use this equation. All right. So then the rest, step 4, 5, 6 is the same like what you learned in chapter 2, 3, and 4, even 5 and 6. You find the individual matrix, you combine them, then you get global matrix. You apply boundary condition, you close the matrix and solve the remaining matrix. You get the temperature. After that, you solve for other remaining parameter. So this one is the same like previous chapter. Only now you focus on temperature alone. Okay. So we look at this tutorial in the next class, right? We stop our lecture here.